dress so fine, through the bumps of dime in your prime. Then you, people call, say beware doll, you're bound to fall. You thought they were all kidding you. You used to laugh about everybody that was hanging out. Now you don't talk so loud.
Here's something you might not have thought about. The magnetic North Pole that compasses point to near the geographic North Pole is actually the south pole of the Earth's magnetic field. That's why it attracts the north poles of magnets. But that hasn't always been true. Today's compasses would have pointed south about 1.1 million years ago, when the geomagnetic north was also a magnetic North Pole. But then the magnetic poles switched places. The magnetic South Pole went north, and the magnetic North Pole went south. They swapped again a little less than a million years ago, and again about 780,000 years ago, giving us today's orientation. Now, if you like doomsday scenarios, you might have heard that we're due for another switch that'll make electronics useless and kill us all. And saying that we're due implies that we know a lot about when and why these swaps happen, which we really don't. The Earth's magnetic field comes from electromagnetic induction, where iron moving in the outer core generates an electric current, with the same physics that power plants use to generate electricity. And that electric current creates a magnetic field. As molten rock reaches the surface of the Earth and cools, any iron in it tends to line up with the Earth's magnetic field. So the iron in solidified lava acts like a time capsule for what Earth's magnetic field looked like when it solidified.
A while ago, while watching a certain superhero movie, I noticed a certain superhero who used magnets to put on his high-tech weaponized suit. I was very intrigued by this and wondered how one could make magnets stronger. And not with the state-of-the-art government research facility, but at home for cheap. I finally decided a testable variable would be temperature, so I asked myself, what effect does the temperature of the magnet have on its strength? And so my Google Science Fair journey had begun. I began to research and soon found that esteemed scientist Pierre Curie had written a doctoral thesis on this very topic. I researched various sources and hypothesized that if the temperature of a magnet is increased, the magnet will become weaker. To test the magnets at various temperatures, I used a freezer, an ice bucket, and a pot of boiling water to bring the magnet to negative 15 degrees Celsius, 0 degrees Celsius, and 100 degrees Celsius, respectively. I also tested the magnet at room temperature. After bringing the magnet to the desired temperature, I tested its strength by lowering it onto a plate of paper clips. I then carefully picked up the magnet and counted how many paper clips it had picked up. My data followed the general trend I predicted. A few paper clips were lost from one temperature to the next, except for the strange spike at room temperature, which could have been my mistake while placing the magnet on the paper clips. But in general, as the temperature increased, the magnet's strength decreased. This is because when cool, magnetic domains, or particles within the magnet that act as little magnets, move very little, so they line up and create a strong magnetic field together. When the temperature, which is the speed of the particles by definition, increases, the particles become less orderly and they don't line up as well, and the magnet becomes weaker. My final conclusion is, as the temperature of a magnet increases, its strength decreases.
While watching the compass needle carefully, we move the switch to the on position. We notice that the compass needle deflects. Again, we move the switch back to the off position. The compass needle comes back to its initial position.
There has been a lot of flip-flopping, since we think that a single flip generally takes a few thousand years from beginning to end. Although there's a ton of variation here too. Reversals could take hundreds or thousands or tens of thousands of years. During a reversal, we think that the existing magnetic field generally weakens until it's almost completely gone.
A magnetic shield. Our sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. If there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
During a reversal, we think that the existing magnetic field generally weakens until it's almost completely gone.
Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. If there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
Since the Earth's magnetic field helps protect us from some of the most extreme forms of interstellar and solar radiation, a reversal would be pretty bad news if it started tomorrow.
Once upon a time you dressed so fine, threw the bumps of dime in your prime. Then you, people call, say beware doll, you're bound to fall. You thought they were all kidding you. You used to laugh about everybody that was hanging out. Now you don't talk so loud. Now you don't seem so proud about having to be scrounging your next meal. How does it feel? How does it feel to be without home? Like a complete unknown, like a rolling stone. Oh, you've gone to the finest school, all right, Miss Lonely, but you know you only used to get juiced in it. Nobody's ever taught you how to live out on.
You're going to see an incredible shot here. This is lightning on the ground, building, preparing to launch airborne. This is enough current to turn the magnetic molecules in molten lava to facing one direction. Here you see the lightning going airborne. After the massive amount of current flew to that spot. You'll see it here again. We will freeze it on the lightning in the ground. Most people don't see this because it happens too fast. But this is a lot of current, and this is what flows through molten lava And this is what's responsible for aligning the metallic molecules in lava.
Some places, like where two tectonic plates have been consistently moving away from each other, have had molten rock coming out and solidifying for millions of years. The farther you get from these divergent plate boundaries, the older the iron-filled rocks are, and the older the trapped magnetic field is. Many of these boundaries are on the ocean floor, so scientists can measure how the Earth's magnetic field has changed over time by bringing sensitive magnetic measuring equipment with them on ships across the ocean. They first tried it back in the 1950s and 60s, and every measurement since has confirmed the same story. There has been a lot of flip-flopping. Rocks of one age will have magnetic north pointing south, just like Earth's magnetic field is today. But other rocks are backwards. Magnetic north points north. The rocks themselves and the iron trapped inside haven't flipped over or anything.
Lonely, but you know you only used to get juiced in it. Nobody's ever taught you how to live out on the street, and now you're gonna have to get used to it. You say you never compromise with a mystery tramp, but now